Konnichiwa. はじめまして、Zac Sweers です。よろしくお願いします。Hi everyone, my name is Zac Sweers. I currently work at Nowhere, and today I'm going to be talking about an open source dependency injection framework I built called Metro. So I published my slides here if you want to follow along. In the meantime, I'll stall time by telling a bit about myself. I formerly worked at Slack and Uber and Flipboard. In the past, I've authored the Dagger Party Tricks blog and talk series. I'm a past contributor to the popular extension of Dagger called Anvil, and the author of Anvil KSP, which is a KSP implementation of it. I'm also the author of a few compiler plugins like Redacted Compiler Plugin, Moshi X, etc., that will become relevant later. At Slack, I tech-led some projects you may have heard of, like Circuit and Compose Lints. And in my free time, I like running, soccer, and fostering dogs. Now, before I get started, a quick poll around the room. Who here uses Dagger plus or minus Anvil? Anyone use Kotlin Inject with Anvil? Anyone use any other kind of DI framework like Coin or... Cool. Anyone not use a DI framework? And the people with their hands up, do you write tests or? Just kidding. All right. So if you're not familiar with dependency injection, DI for short, which is what I'll say for the rest of the talk, fear not, because I'm going to start with a bit of an extended primer. So what is dependency injection? First, let's look at an example. Let's consider a simple weather app. It's basic, you give it a location, and it gives you the forecast for that location. Our weather app is composed of a few components: a weather service that we see here that can talk to a weather API, a weather formatter that can format the responses into a localized format friendly to the user. And it's simple. It prints the formatted forecast for a given location when we run it. Now, in a trivial implementation, we might just take these and make them into properties of the class. However, you might already see some problems. Maybe our weather service is used in multiple places. We are a weather app after all. A popular pattern for this becomes the singleton. It's just as hard to test, but at least now we're limiting instances. If we want to make this testable, we have a few options. Maybe we add some set service backdoor here. It's powerful, but it's prone to leaks. If you have multiple levels of this, it very quickly becomes unwieldy. Suddenly, they are surprisingly mutable, and you, the consumer, have to know an awful lot about the wiring of these dependencies, and it only fails at runtime. So maybe we use a service locator. Could be as simple as get application get weather service. Get application in this case could really be any service holder. Replace this with by injector.instance or by inject, or the locator service of your choice. Locators are still hard to test, though, because you do have to backdoor it in somewhere. And what's worse is they are only validated at runtime if they're validated at all. The last and best option, though, is to just make it a constructor parameter. This doesn't even technically need a DI framework to use it, and is often just called manual DI. In manual DI, we deal with just constructors most of the time. If you know the language, you understand the code you're reading. This is a textbook example of the programming concept called inversion of control, or my preferred description, the Hollywood principle. Don't call us, we'll call you. Aside from the standard language features, the kicker here is that you don't need to know where that dependency comes from or how it's wired up for you. In a test, you just new it up. If you want to fake the data, give a fake weather service. It's implicitly validated at compile time because you literally cannot compile if you don't pass these dependencies along. No needing to fish things out of a bag at runtime. Manual DI isn't free, though, because we still have all this boilerplate somewhere. It scales up pretty quick, too. Your service likely needs an HTTP client, which in turn likely needs a cache. This is really where a DI framework comes in. So, without further ado, introducing Metro. Metro is a compile-time dependency injection framework that draws heavy inspiration from Dagger, Anvil, and Kotlin Inject. It seeks to unify their best features under one cohesive solution while adding a few new features along the way, and is implemented as a Kotlin compiler plugin. So why another DI framework? Well, it's felt for some time like the Kotlin community has been waiting for a library that unifies the best of Dagger code gen, multiplatform, Anvil aggregation, works as a compiler plugin, has fast IDE support and linting, and is Kotlin first like Kotlin inject. Different solutions exist for different parts of these, but there's not yet been a cohesive and unified solution that checks all these boxes. It's also a lot of domains that I've worked into, and I guess at some point I decided that that was me at the intersection of all that. So in short, Metro stands on the shoulders of giants before it. It doesn't seek to reinvent the wheel. It tries to build on top of what existing solutions do well. And the goal is a solution that unifies their best ideas into a one-stop shop. To start using it, all you need to do is apply its Gradle plugin, and you're on your way. Metro builds on top of established patterns from existing DI frameworks with familiar semantics like different injection types, providers, multi-bindings, scopes, and intrinsics like provider and lazy. Like other DI frameworks, Metro lets you use annotations to indicate dependency semantics in your code directly, allowing you to replace this wiring with this. The primary entry point here is a dependency graph. All you need to do is define types or type keys you need, and it will manage instances for you. Metro's compiler plugin will implement it at compile time, following its dependencies from the roots in your graph. Graphs are analogous in Metro to Dagger and Kotlin injects components. Creating a graph is easy using a magic typed create graph function. This is a compiler intrinsic, meaning the source is just a stubbed body, and the compiler replaces the call at compile time, similar to the standard library's typeof function. If your graph itself has inputs, you can create a factory interface annotated with @dependencyGraphFactory with a single abstract function that takes any input parameters and returns the graph. Parameters must be annotated with either @provides or @includes. @provides annotations or @provides annotated parameters will be directly available on the graph as simple instance bindings. Includes we'll get to later. Then you can just call create graph factory, and the compiler will again replace this with a call to the created factory implementation. Let's look now at how we get other bindings into the graph. The simplest way to provide a binding is what's called a provided binding, which is just a function on the graph annotated with @provides and returns a type. That type is then available on the graph. Provided bindings can have dependencies. You just add them as parameters, and Metro will stitch them together accordingly. Providers can also be inherited from supertypes, allowing you to define common interfaces and reuse them in different graphs as needed. If you want to provide multiple instances of the same type, you can disambiguate them with qualifier annotations. Qualifier annotations are meta annotations, meaning they are annotations that go on other annotations. A convenience built-in one is called @named, and that just takes a single string argument. The pair of the binding type and its optional qualifier are what is called a type key. Metro views and validates all bindings on the graph by their type key. What is a binding? Inside Metro, each type key on the graph is modeled by a binding. We covered one type @provided, and we'll cover a few more in a bit. Binding is the managed instance keyed by its type key, and a dependency is any binding that is depended on by another binding. And it's more about the relationship between them. Most of this talk will talk about things in terms of bindings, and with that, we'll look at how injection works. If you own the class, you can skip provides and just annotate the class directly. The typical way you would make a class injectable and available on your graph is to annotate it with these @inject annotations. In simple cases, you can just put them directly on the class itself, or if you have multiple constructors, you can annotate a specific injectable one. This, in turn, is another binding type, a class type, or a class binding. This gets us pretty close to our original example, but in this trivial example, this alone isn't saving us that much code. Where a framework like Metro or Dagger or Kotlin Inject, etc., really shines is when its native features start making the tedium easy. So let's do that, starting with scoping. Like Dagger and Kotlin Inject, Metro supports scope annotations. These indicate the scope or lifetime of the binding, and it must match the graph that they attach to. That is to say, this tells the compiler to ensure that only one instance is ever created in that graph's lifetime. First, our graph must declare its scopes. These are also meta annotations, and Metro's standard scope annotation is @in, which takes what's called a scope key k-class argument. Metro also supplies a common app scope key class. These combine to make @in on our app graph. Single-in app scope is lifted from Anvil and essentially Metro's analog of Dagger and Kotlin Inject's @singleton annotation. It's a little more explicit and also reusable with different scope keys. Now that our graph declares scopes, we can use scoped bindings in it. Going back to our example, scoping the weather service just becomes, is like we needed before, is now as easy as just adding this scope annotation. This scopes a single instance within the lifetime of our graph. Anything in the app graph or its extensions will always get the same lazily initialized instance now. Like Dagger, all bindings and graphs are unscoped by default. Scoped bindings are lazily initialized with thread-safe doubly checked locking. The scope is declared at the binding site rather than the consumer of it needing to know about it ahead of time. And certain binding types can't be scoped, and we'll cover those later. We've covered class and provided bindings. One unique thing with Metro is, one unique thing that Metro can do is these can be private. So in source-based code gen like Dagger and Kotlin Inject, everything the compiler generates code for must be at least package accessible. Since Metro operates as a compiler plugin, it can modify the code directly. Now let's cover the remaining binding types. Next up is an optimization called @binds. Just like Dagger, these callables are like aliases. They're simple abstract functions or extension properties that act as a pipe to say that this binding is actually just an alias to this other binding. As such, they must be type assignable. Metro never generates any code for these declarations and uses them purely as compile time signal. Since they're just an alias to their alias type, they also cannot be scoped. Common use cases include binding implementation types as interfaces that they implement, binding types into multi-bindings, which we'll get to, binding types as nullable variants, which is something that Metro natively supports since it's a Kotlin language feature, and binding types with different qualifiers. Next, let's talk about assisted injection. In some cases, you may have a class that requires a runtime dependency to be instantiated. For example, consider an injected user repository that needs to know about a user ID to be constructed. We could put this ID on the graph, but it's not really something we need on the graph. We may also want to create multiple repositories with different IDs. So to support this, Metro has something called assisted injection. To do this, you mark which parameters are assisted with the @assisted annotation, and add a simple factory interface annotated with @assisted factory that has a single abstract function with matching assisted parameters. These parameters must match the constructor's assisted parameters, and this SAM function must return the assisted type. And now you can inject this factory, and Metro will generate code to handle shepherding the assisted parameters to the constructor injected type. The last major binding type is multi-bindings. Multi-bindings are collections of bindings that are aggregated into sets or to maps. Contributing is easy. Just annotate them with @into_set or @into_map. The underlying binding on the graph is created automatically. The underlying multi-binding on the graph is created automatically if any of these into annotations are present, but you can also declare them directly with @multibinds. The Metro compiler will implement these getters, so you can just call them directly. Unlike Dagger, Metro will error by default on empty declared multi-bindings, and you have to opt in to allow empty ones. Sorry, I was off by one slide there. For map keys, keys must be statically defined at the binding site with a map key annotation. Map keys are the final meta annotation in Metro, and you can define custom map key annotations with it. Again, there are some built-in ones you can use here, like @class_key or @string_key, etc. If you have a collection you want to contribute into a set, you can also use @elementsIntoSet, and we'll contribute them all at once. Next, let's talk about aggregation. So who here uses Anvil or Dagger Hilt? So Metro has Anvil-style binding aggregation built in as a first-party feature. No more needing to have an intermediary at merge component annotation or anything similar, nor do these tools need to try to preempt the graph generation by running in some earlier stage of the compiler or build. Aggregation works by aggregation scope keys. These are the same keys that you would use with something like @in for allowing for shared semantics. This is the Metro way of saying aggregate all bindings contributed to this scope. In fact, if you declare an aggregation scope, you don't even need to include the @in annotation as it is implicitly added. What is a contribution? There are 3 types. First, let's consider a graph that wants to expose a cache. A cache is an interface, and we have an injected implementation available. Metro can discover this automatically, but its type is technically cache impl, not cache. We could add a @binds property, but we already know at the implementation site that we wanted to expose as the cache type. This is where we introduce our first contribution type, which is contributes binding. Contributes binding contributes @binds bindings for that class as one or more of its supertypes. Under the hood, Metro generates a contribution interface that the consuming graph just extends. If there's multiple supertypes or an ancestor type, you can also explicitly define it. If you're familiar with Anvil, this mostly works the same, except the bound type is more flexible. Metro uses a binding semantic that looks like a function call, but is actually a class. Since we're a compiler plugin, we can easily read this generic type argument, and it allows the developer to declare things like generic or nullable types here. The compiler will validate at compile time that the annotated type extends or implements the defined bound type. And if you have just a single supertype, you can omit the binding altogether. If we want to contribute into a multi-binding, we can do that too. Contributes into set, contributes a class into a multi-bound set of its supertype. Maps are similar, just annotate the class with the map key as well. The third and simplest type is contributes to. Maybe we want to define these handlers in some other interface and just make sure the app graph extends that. Contributes to just contributes the annotated interface to that scope, and the graph will extend it. As long as these classes are visible on the class path to the graphs that declare that scope, the Metro compiler will automatically aggregate and include them directly in the generated graph. This is super useful, if not necessary, when working in a larger modularized code base. Like Dagger, Metro supports injection of bindings wrapped in intrinsic types, namely provider and lazy. These are useful for deferring creation and initialization of dependencies. This only needs to be requested at the injection site. Metro's CodeGen will generate all the necessary stitching to fulfill that request. Provider is like Dagger's provider. It is a simple interface whose invoke function calls, or whose invoke calls returns an. Give me one sec. It is a simple interface whose invoke call returns an instance every time. If the underlying binding is scoped, then the same scoped instance is returned each time invoke is called. If it's not scoped, then it always returns a new instance. Lazy is the Kotlin standard library's lazy. It lazily computes a value the first time it's evaluated and is thread safe. Note that lazy is different from scoping in that it is confined here to the scope of the injection site rather than the graph instance itself. There is functionally no difference between injecting a provider or a lazy of a scoped binding. The underlying implementation in Metro's double check prevents double memoization in this case. The last thing I want to cover in this prolonged primer is graph extensions. If you're familiar with Dagger subcomponents, this is the same concept, but with a hopefully more obvious name. Graph extensions are graphs that extend other graphs. You declare them with @graphExtension and then declare an accessor for them in their parent graph to tell Metro to generate them. Like regular graphs, graph extensions can also have factories that you can declare instead. The parent graph can also implement these factories. They can have scope annotations. They can have aggregation scopes. They can have provider and binds callables. And they can even have their own chained extensions. Okay, that was a lot. I'm going to take a quick water break on this. All right, so there's a lot of neat advanced features that I'll touch on at the end, but I want to pause there and return to the original example again. So let's hop on the build train here and follow how Metro runs these tracks in the compiler. First, let's look at a conventional Gradle build pipeline. In the simple case, you just have a compile Kotlin task. If you're multi-platform, you'll output multiple different binaries. Now, if you run KSP, this runs first and generates sources that then go into compile Kotlin. This is what the Anvil KSP or Kotlin inject pipeline generally looks like. If you run capt, you actually get two precursor tasks, one Kotlin compile task to generate Java stubs and one Java C task to run Java annotation processing. Then its outputs are piped into the compile Kotlin task. If you have any Java sources, you also get a compile Java with Java C task at the end. And in complex cases, such as Dagger compiler, then you can end up with 4 stages of stub generation, capt, compile Kotlin, and because Dagger generates Java, compile Java task. That's 2 Kotlin compilations and 2 Java compilations in just one project. If you use Dagger Hilt, its Gradle plugin actually adds another Java C call at the very end, so that's 5 compilations. And if you generate anything with KSP, that becomes a 6th, which I do not have room for on this slide. And that's just one module. In a modularized code base, this gets multiplied by n number of modules in your project. And this obviously isn't ideal. Large teams will usually try to mitigate this impact by limiting how many modules apply capt. This was also a big appeal of Anvil, as it allowed you to offload some of this work that Dagger compiler did via its factory generation feature. In Metro, all we ever have to do is one compilation. This alone makes it much faster than the above scenarios. And on top of that, it generates IR directly, no sources. How much faster, you ask? Up to around 40 to 70%, depending on your setup. There's a benchmark project in the repo, and there's also some shared testimonials from other companies that have adopted it on the documentation site. So let's explore the phases of this pipeline. There are 2 primary phases, the front end and the back end. Each of these have roughly 2 interphases with a translation layer in between. Let's break these down in order and what Metro does in each. The front end is focused on parsing sources, reporting diagnostics, and building a resolved front-end IR, aka FIR, representation of the Kotlin code that is ready to be compiled. It's a tree structure representation of the Kotlin code. Source files go in, the parser reads these files and loads a PSI representation of them. That's the same PSI that runs in IntelliJ, the same PSI that lint checks are built with. And this is basic tokenization to build an FIR tree and shakes out syntax errors. Once FIR is constructed, a wealth of checkers run over the FIR tree to report diagnostic issues, like literally a couple hundred at least. Because this all runs in the IDE, these show up right in the IDE. FIR was introduced in K2 to streamline the compiler front end, significantly improving compiler performance along the way, unifying the model the compiler and IDE ran, and making it much easier to introduce new language features. The front end is also pluggable. In K1, there was something called analysis handler extension, which I'm not going to cover here, but it's worth mentioning that's what Anvil was built on top of and why it was so much faster than capt for factory generation at the time. It's also what KSP1 was implemented on. However, this hook was really only generating new sources. Even in Anvil's case, it would generate new sources and then run the front end multiple times. K1 didn't support custom diagnostics as far as I know. In K2, there's a fully fledged plugin system for generating new declarations, transforming them, and custom checkers built on top of FIR, and Metro uses these extensively. Metro does 3 types of mutations in FIR: declaration generation, supertype generation, and status transformation. As you could expect, Metro generates a ton of different declarations. Constructor injector classes and providers get generated factories that graphs call to create instances. Here we see another benefit of Metro, where we can modify these classes and generate new classes within them. This is why Metro can inject private constructors or call private providers. Assisted injection needs to create factory implementations. Contributed types generate a nested contributor interface that will host @binds declarations, et cetera, graph creators, member injectors, a few other things run in here. Most of these declarations implementations are generated later in IR, But in order for them to be visible across modules, they need to be visible in Kotlin metadata. And in order for classes to be visible in Kotlin metadata, they need to be visible by the end of FIR. So we generate these header signatures for these classes in FIR for metadata, and then we implement them in IR. In the IDE, you can also see these declarations. Supertype generation is a callback we get during FIR construction to generate additional supertypes onto a given class. This is the hook we need for Metro's aggregation features. Skimming over the implementation details, but it allows us to tell FIR that these classes should be supertypes. Even though these classes may not be implemented yet, just denoting their supertypes is enough to satisfy the compiler here. A neat newer IntelliJ feature is it will show contributed supertypes in the IDE too, and you can technically even skip doing typecasts. Finally, we have status transformers. Status, as a concept in Kotlin, is this batch of modifiers in a declaration. It also includes modality, think open, final, sealed, and visibility. Metro has two. The first transforms providers to always be private, allowing you to write them without a visibility modifier, but transforming them to be private at compile time. The second adds an override modifier as necessary to an accessor if a contributed supertype has a matching accessor. FIR generation is extremely finicky because FIR has life cycles. Remember, this runs in the IDE, so you don't actually know if a function doesn't have a return type or if the user just hasn't finished writing it yet. As a result, Metro tries to limit what it does here just to the necessary stuff. Metro even has some features that rely on IDE visible FIR generation, but those are behind flags for reasons I'll explain at the end of this section. After FIR generation is done, we enter the checker phase of FIR. Checkers are basically helper diagnostics that make sure you're holding it right. Think things that are syntactically valid but programmatically wrong. A simple example of one is to make sure that a dependency graph factory has a single abstract function, that function returns a dependency graph, and that function has valid parameters. And Metro has nearly 100 of these checks just to make sure you don't accidentally do the wrong thing and try to bounce you in the right direction. Since this is all in the front end too, they appear fast as it's early in the compilation. And again, since FIR runs in the IDE, they can also show up right in the IDE. I do need to put a huge caveat here at this point. Metro's IDE support is currently best effort. Enabling it requires toggling a custom registry in IntelliJ, which is easy enough. The hard part is that the version of Kotlin that ships in the IDE plugin does not necessarily match the version that you're building with. It doesn't even necessarily match any stable release of Kotlin because the Kotlin IDE plugin regularly just takes cuts from the head of the Kotlin repo. Because of that, IDE support is very much just for the adventurous for now. There's some ideas on how to make this more reliable and resilient to breaking API changes in the future, but for now, this is how it is. The docs for enabling it are on the site if you're feeling adventurous. Now let's talk about the backend. Up to this point, all Metro's plugins have done is create basic headers for classes and merge contributions. Now we're getting to the fun part, graph generation and graph validation. The Kotlin compiler backend speaks a structure called IR, and an FIR to IR phase runs to convert FIR trees to IR trees. In the backend, we have two phases. IR transformation, where transformers transform IR code across multiple rounds to optimize known programming patterns and generate extra IR code. IR lowering is into target platforms. Each supported platform converts IR into their platform's binary format here. Metro doesn't do anything in IR lowering, so I'm only going to focus on transformation. At a high level, IR transformation could be thought of as the implementation details and where the brains of the compiler live. This is the phase that implements the bulk of the code, ranging from desugaring language features we love into more primitive constructs to optimizing common patterns into more efficient alternatives. IR is a fair bit older than FIR, having gone stable in Kotlin 1.4.3. This is also the phase that Anvil's contribution merging ran in. However, in K2, this no longer runs in capped stub generation, which is why Anvil was never going to be able to work with K2 and Dagger. Metro's IR transformation runs in two parts. First, it generates those binds functions we generated in FIR for contributing types. Along the way, we also collect information about all of the contributions. And second, it transforms everything else. At a high level, Metro's pipeline in this phase can be described like this. Step 1, transform non-graph classes. These are simple mechanical implementations for things like factories for constructor injection. Step 2, we process dependency graphs. 2A, we collect graph data, available bindings, roots, extensions, etc. Then we process extensions, which may recurse back to go into step 2. We then build a binding graph. This is the graph data structure within Metro that holds bindings and can validate them. Then we seal the graph, wherein we populate bindings starting from the parent's roots as well as what the child graphs asked for. Runs a hybrid targen plus con algorithm to detect cycles, safe cycles, and perform a topological sort. And finally produces a result of the sorted, reachable, and deferred type keys in the graph. And if we get to the end of this, the graph is valid, and we start implementing the IR graph class from it. So let's go back to our weather app and piece these into how they're modeled in Metro's IR layer. First, we peel off some metadata about the graph, like its scopes. Then we read off its available providers and binds. And finally, its roots. In this case, our root is just the weather app class. As we populate dependencies from it, we discover and add these bindings. Is this moving? No. Sorry, there we go. Continuing to trace from their dependencies. There we go. In graph extensions, they are processed first and get access to a parent context that gives info on keys available in the parent that they can mark as used and reserve a field for. Once populated, we start validating with Targen's algorithm. This works great because if we do encounter a cycle, we get a nice backtrace of elements in the cycle, and we have easy hooks to indicate if it's a valid cycle or not. For valid cycles, we track deferred keys here. Once we finish Targen, we have a graph of validated vertices and edges that we know is a valid DAG. We then take this and pipe it into Con's topological sort algorithm to produce a list of topologically sorted keys. This can be thought of as the required order we need to initialize bindings in the graph, starting with bindings that have 0 dependencies. When we pop out of graph sealing, we're ready to generate graph IR, such as the Metro graph implementation code. This part is fairly simple. First, we generate fields, starting with any input parameters from our factory, if applicable, and fields for this graph instance. Then we run our sorted keys through a provider field collector that returns a sublist of keys that we need fields for. This is primarily going to be scoped bindings, but may also include some other types. Our weather app has these. Because weather service is scoped, we wrap it in a double check to ensure that it is memoized. And any that don't need to go in fields can just be created at the injection site. Then we go and implement any binds callables or roots. Binds callables just get stubs, and for roots, we generate binding code either that invokes that binding or the provider field if one exists. And now you have a usable graph. There is some other stuff that happens in IR that I won't get into here but are worth mentioning. Incremental compilation is something we have to consider, including generating code in a way that ensures the graph is recompiled if the user changes some relevant code. This comes up most often with annotations, which don't trigger recompilation by default on their own. We also transform those create graph and create graph factory calls in this layer to just call the created graph directly. So what happens if validation fails? So one of the common struggles with DI frameworks is deciphering their error messages, and Metro tries really hard to give useful error messages. Not only detailed information about the context of the error, but also what you should do about it and hints for things that may be related. So for example, if you have a missing binding, but Metro sees similar bindings on the graph, for example, the same type with a different qualifier, it will include them in a list at the bottom of the error message. If you have a cycle, Metro will report the full cycle and usages of those dependencies so that you can trace it. And if you try to inject an assisted type, it will tell you about the assisted factory it thinks you probably want instead. And so on and so forth. There's a bunch of these in the IR phase as well, and it will greedily try to give you practical but detailed information about what to do in that situation. And remember, this is all in addition to the 100 or so checks we have in FIR. Now, there's a ton of advanced usage that I don't have time to cover today. Add includes, member injection cycles, a whole bunch of these, just to name a few. If any of these look interesting to you, please go check out the doc site for it. I do want to cover a couple more things here before we finish out. One is interop and adoption. So now maybe you're looking at all this and thinking like, gee, seems nice, but my code base already has a bunch of existing stuff, and migrating is a huge cost, and I don't have that kind of time. So the good news is that Metro has excellent interop with existing Dagger, Anvil, Kotlin Inject APIs, and that interop can come at different layers too. In the simplest case, you can interop at the per graph and per component level by just doing basic add includes dependencies on each other. Metro won't know anything about the Dagger nature of the interface and vice versa. I know we didn't cover it, but this is how you do the Metro equivalent of component dependencies. It works really well for interop between subprojects and can also work bidirectionally. To migrate directly onto Metro while minimizing source changes, you can enable interop in the Gradle plugin with Dagger, Anvil, and Kotlin Inject annotations. What this means is that you can reuse almost all of your existing annotations without needing to change much in your source. These annotation types are fully replaceable, so you could get mileage from any other DI frameworks or even bring your own annotations. There are still some minor cases that require manual migration, but they are all documented on the adoption section of the site. For Dagger, there is an extra level of runtime interop that allows Metro to interop with Dagger's provider, lazy, and members injector types as needed too. Metro also understands most of Anvil's annotation APIs, including ones like rank and ignore qualifier that don't actually exist in Metro's own first-party API. You can also replace these annotations with whatever you want, so it's all customizable via the Gradle DSL. If you have custom code generators, you should be able to use most of them with Metro, depending on how you've implemented them. If you are generating with KSP, this will almost certainly just work out of the box with annotations interop. If you wrote custom Anvil code generators, you will need to migrate them to something else, likely KSP. The good news is that you can do that first, still have it work with Anvil, allowing you to split up the work as you're doing it. For a full migration, there are a few strategies you can do, and they are documented on the doc site here. Unfortunately, short on time. Lastly, I want to address a few frequently asked questions and also some future plans. So in the FAQ, are compiler plugins safe to use? And the answer to that is they're stable for use. The API is unstable. That said, it's fairly straightforward to maintain releases. I try to release them within same day, and we get plenty of pre-releases as well. Sorry, translators, that was not in the doc. It is a solo maintainer project, like much of open source. But I wouldn't say that I work on it alone, and I have a lot of help and contributions from people, including people who worked on Anvil and Dagger. There's currently not an SPI API like Dagger's, but it has something that it's something that I'd like to add. And debugging is definitely different since there's no source generated that you can inspect or debug. But you can enable reporting today and see graph dumps and a ton of other details. In the future, Metro doesn't currently have an implementation of Dagger's fast-init option, which uses a mechanism called switching providers under the hood. It's something I'd like to add eventually, though, and I'm open to PRs. I'd like to explore potentially writing a dedicated IDE plugin and add in-IDE navigation support, as well as improved IDE support for diagnostics. Dynamic and ad hoc graphs are a neat Metro feature that's on the roadmap for 0.7 that'll let you create dynamic graphs and do easier test overrides. And Kotlin 2.3 is going to unlock a bunch of new features via some new APIs for top-level declaration generation. The biggest one will be fully supporting multi-module aggregation in multiplatform and optimizing incremental compilation for contributes binding cases. And that's it. Thank you all for coming to my talk. Please give Metro a try if you haven't. I'm really proud of how far it's come in a short time, and I think its future is bright. There's a ton of samples in the repo. The doc site is there with both extensive markdown docs as well as API kdocs. I'll be around for a little bit for the Ask the Speaker if you have any questions. Also, feel free to talk to me if you see me around the conference or hit me up on Blue Sky or Mastodon. Arigato.